Hello, hello, hello. In this episode of What's the Big Idea, we're going to be talking about Schrodinger's cat, the famous quantum mechanics paradox of Schrodinger's cat. And we'll talk in that context about the concept of pure quantum mechanical states and mixed quantum mechanical states. These ideas, as you'll see, lie at the heart of trying to unravel the paradox of Schrodinger's cat. Erwin Schrodinger, as I'm sure you know, was one of the founders of quantum mechanics. You spent a good deal of your time in Physics 302 studying his famous equation. He was a contemporary of Einstein's, and like Einstein, he was a rather philosophical person. And like Einstein, even though he was one of the founders of quantum mechanics, he was pretty deeply uncomfortable with some of its philosophical implications. And the idea of entanglement bothered Schrodinger just about as much as it bothered Einstein. And as a way of sort of summarizing his discomfort with the idea of entanglement, he took the sort of case that we've been talking about, where quantum mechanics has this idea that quantum particles can exist in an entangled state, such as this one here. And he tried to imagine what would happen if you extended this sort of argument to more macroscopic particles. And his famous experiment, thought experiment, was to imagine the following situation: a sealed box inside of which was a cat and a vial of poison and a little mechanism that had a radioactive atom in it. And the mechanism was such that when the atom decayed, it would release a chain of events, causing this hammer to fall and break the vial of poison, and the poison would be released into the box, and the cat would die. So until you look inside the box, if you take the idea of quantum mechanical entanglement seriously, uh, until you look inside the box, the argument goes, the quantum mechanical state of this system here would be a superposition, an entangled superposition. In one of the elements of the superposition, the cat was alive and the atom undecayed, and in the other element, the atom had decayed, causing the cat to die. So Schrodinger said, well, this would be the correct quantum mechanical description of the system before you looked. So the cat we can must think of as being in a superposition of being alive and dead. And of course, the point of this story was to highlight what Schrodinger thought was an absurd implication of quantum mechanics. It's absurd, he reasoned, to think of a cat being both dead and alive at the same time. And as you ponder the paradox of Schrodinger's cat, one thing to keep in mind is the famous correspondence principle of quantum mechanics. And what the correspondence principle basically says is that quantum mechanics we generally use it to describe microscopic systems where it works well. As systems become more macroscopic in size, we know that classical physics provides an accurate description of macroscopic objects. So the correspondence principle basically says, well, as systems become macroscopic, the predictions of quantum mechanics must begin to agree or approach those of classical physics. So somehow, in reasoning through the situation of Schrodinger's cat, we're going to have to keep in mind this correspondence principle and try to understand how quantum predictions must approach our everyday common sense experience, in which cats are neither both dead and alive, they are either dead or alive. So, up until now, we've dealt pretty much exclusively with what we can refer to as a pure quantum mechanical state. When we write down something with a wave function, that's almost by definition what we mean by a pure quantum mechanical state. So this entangled two-photon state is just one of many, many examples of a pure quantum mechanical state. And we would describe this pure quantum mechanical state as a superposition of this state HH and VV. It's sort of a 50-50 superposition of a state in which one of the states in the superposition, the two photons are both horizontally polarized, and the other state that makes up the superposition, the two photons are vertically polarized. And as you now know, if you've read the Dellinger and Mitchell American Journal of Physics paper that we've been reading about experimental tests of Bell's inequalities, it's a little bit tricky to create such a pure entangled state. The way we do it is you have two very thin crystals, either one of which on its own would create one or the other of these states. And if you set up a situation in which, in principle, you can't tell which of the two crystals the two photon pair was generated in, then the correct way to describe that state is as a superposition that looks like this. The situation should remind you of, it's very similar to what we saw when we looked at single photon interference, where if the paths are indistinguishable, the right quantum mechanical way to describe the state of in the single photon interference experiment is as a superposition of photons having gone one way or the other. And as I said, it's sort of tricky to get this indistinguishability. You have to make the crystals very thin, and you have to do other tricks to make it so that, in principle, you can't tell which of the two parts of the crystal the two photon pair was generated in. And if you're not careful, what you'll end up with is what we refer to as a mixed state, which is sort of a much more classical thing, which is, half the time the two photon pair will be generated, say, in this part of the crystal, which generates an HH pair, and half the time the two photon pair will be generated in the right side of the crystal, which generates a VV pair. So as we said, pure quantum mechanical states, entangled states, tend to be very fragile. So when you go to try to build systems that take advantage of entanglement, very often, even though you're trying to create entangled states, you end up with mixed states. And understanding how to deal with mixed states is actually an important part of understanding how to do things like build a quantum computer. And it's important to realize that even though these two states look, sort of superficially similar, they're in some sense 50-50 mixtures of the same thing. The results that they will produce in some experiments are actually quite different. So to take a specific case, let's imagine in our standard setup here that we set both the signal and the idler polarizers to be at with their measurement axis oriented at plus 45 degrees. Well, then if you apply our standard methods for calculating these joint probabilities, you'll find out that if you have a situation that's in this pure entangled state, and you send it in, half the time you will find both the signal and the idler photon come out the top port, and half the time the signal and the idler photons come out the bottom port. They either both come out the top or both come out the bottom. If you ask what's the probability that the signal will come out the top port and the idler will come out the bottom port, that's this joint probability. That's zero, never will happen. And the same thing if you ask what's the probability of the signal photon coming out the bottom port and the idler photon coming out the top port, joint probability zero, ain't gonna happen. On the other hand, for the mixed state, half the time you're in this HH state, and in that HH state, there's a 25% chance of each of these four different outcomes, and the same thing for the VV state. So overall, the probabilities of what you're going to observe are 1/4 for each of these four different possibilities, quite different from when you were dealing with the pure entangled state. Now, as we make our way to trying to understand what all this has to do with the Schrodinger's cat paradox, the next thing I want to point out is that when we write down a pure entangled state, like this one, the one that we've been dealing with, which we'll now start calling phi plus. This is, as we've said before, one of the four Bell states. The plus here derives from this plus here. And when you go and do calculations of things like the joint probabilities, this plus sign here is key. So the joint probability P of theta sub s comma P theta sub I is, we've calculated previously, is this expression here. And if you follow through the derivation, the plus sign here ends up corresponding to the plus sign here. And that plus sign means that if, for example, you set the angles of the signal and Idler photon analyzers to be the same, you're going to get a 1/2 as the net result, because cos squared theta plus sine squared theta is 1. On the other hand, if you consider another of the Bell states, phi minus, where you have a minus sign here and you follow the derivation through, it's pretty obvious that this minus sign here, you can follow it through, and it ends up being this minus sign here. And that means that the joint probabilities that you calculate are going to be quite different. So, for example, if you consider the special case, whoops, wrong color. If you consider the special case in which the signal and Idler analyzers are set to the same angle, you're going to get a 1/2 cos squared theta minus sine squared theta. And that is going to be 1/2 times cosine 2 theta, which is quite a different result from the one you got here. In this case, you've always got a half as the joint probability. Here, you get something that varies depending upon what theta is. So that's just one specific example of how a small change in sign can lead to results that are quite different. And now the thing to note is that these states phi plus and phi minus are really just special cases of a more general state of this form that has this factor of e to the I phi. And phi is what we mean when we talk about the relative phase. The relative phase between this part of the state and this part of the state. So when the relative phase, for example, is 0, e to the I 0 is 1, and that corresponds to a plus sign. And when the relative phase is pi, e to the I pi is -1, so that corresponds to this particular case where you get a minus sign here. But more generally, phi can be anything, and you can have states of this form that have any relative phase that you can imagine. And just generally speaking, the value of the relative phase really matters, because when you calculate things like these joint probabilities, the results that you get vary depending upon exactly what the relative phase is. So what's all this have to do with Schrodinger's cat? Well, let's find out. So if your system consists of a cat plus this mechanism with the vial of poison and the radioactive atom, the general way to describe the quantum mechanical state of that system is as a superposition that looks like this, and there is in general, a relative phase that enters into the description of the quantum mechanical state of the system. And now if we try to think about the difference between our cartoon version of the situation and what the situation would be in the real world if you had a real cat and a real bottle of poison, um, there is an external world here, and inevitably there are going to be interactions between what we've put inside the box here and the external world. And it turns out that inevitably those kinds of interactions are going to cause fluctuations in the relative phase. So in the real world version of events, phi would not be a constant. Phi would be a time varying and typically a randomly varying variable. Well, what are the implications of that? Well, remember the case of the experiment with the two holes? It's the same thing. Let's go back to our example of single photon interference because the situation there will be illuminating. So remember the experiment that we can set up to observe single photon interference involves building a Mach-Zehnder interferometer, and you have a single photon that enters in, and it has um, two choices, so to speak, to make. It can get to the final detector via two different routes, and the phase difference between the two routes ends up appearing prominently in our expression for the probability that the photon will be observed at detector located at port A of this beam splitter. So we get this um, oscillating function of the phase difference, delta. And experimentally, the way we vary that phase difference is to move this mirror back and forth. And in this experiment that we're showing here, we're being quite intentional about it. We have this mirror mounted on a mount with a piezoelectric transducer on it. We can slowly vary delta in a very controlled way and observe this nice interference effect. And specifically, what we're doing is we set delta to a particular value, and then we count photons that arrive within a certain interval of time. We record that count, and then we move on to a different value of delta, count for the same period of time, and see how the number of photons that we've counted changes as a function of delta. Well, now imagine, if you will, that suppose delta was not being varied in this nice controlled manner. Imagine this mirror was mounted on some sort of not particularly rigid mount, and there are vibrations in the room, people knocking against the table, and so the mirror is fluctuating back and forth in sort of a random pattern. Well, then if that random fluctuation occurs on a time scale which is short compared to the amount of time that we're sitting and counting the photon arrival, the effect of that will be to wash out all this nice controlled variation. And in that case, what you would see is that you would not be able to observe this interference pattern. And so let's go back to the case of Schrodinger's cat. We may want to think in our idealized world as the system being in this pure quantum mechanical state. But due to interactions with the external world, the relative phase of the components that make up this pure state is going to vary over time. And in the real world, with macroscopic systems, those fluctuations are going to occur on an incredibly fast time scale, picoseconds, femtoseconds, something like that. There's going to be this jiggling back and forth, much the same way that the mirror in our Mach-Zehnder uh, um, interferometer, if it's varying back and forth, it's going to wash out all of these interference effects. Well, the effect in Schrodinger's cat is going to be similar. Due to interactions with the external world, phi varies, and we're going to end up with a situation in which sort of the cross terms that appear when you go to calculate various things from this wave function um, average to zero, and the situation ends up being essentially the same as this mixed state, which is a 50% chance that the cat is alive and the atom is undecayed, and a 50% chance that the cat is dead and the atom uh, has decayed. Um, so this process in which the fluctuations in phi cause sort of the pure state to essentially be indistinguishable from a mixed state, that process is known as decoherence. Decoherence. And decoherence is really at the root of trying to understand what's going on in the Schrodinger's cat paradox. In a real situation, decoherence causes the situation essentially to be what our classical intuitions would expect, which is that either the cat is alive or it is dead. And this is, as we said at the outset, a manifestation of the correspondence principle. Correspondence, correspondence principle, remember, tells us that in the limit of macroscopic systems, classical physics works well. So with a real cat inside a real box, it's perfectly correct to think of the cat as either being alive or dead. So you can say it's not curiosity that killed the cat, but rather decoherence, which may have killed the cat or may have left it alive. So that's it for this episode of What's the Big Idea? Hope to see you again soon. Bye bye.